Today we're going to look at section 2.7, dealing with absolute value functions and graphs. That's our whole objective in 2.7. Can we graph absolute value graphs? Okay, we're going to start out with some basic ones, and then I'm going to show you some shortcuts to make the graphing a little faster. Okay, so absolute value functions. Our parent function would just be y equals the absolute value of x, or f of x equals the absolute value of x. The shape of that graph is a V. Parabolas have more of a U shape, absolute values have a V shape. It is symmetric. There's a line of symmetry called the axis of symmetry that goes right through and cuts that graph into two mirror images. Okay? Just like a parabola has a line of symmetry. There's a single point that we call the vertex. It is the maximum or minimum. And you might say, well, how can it be either one of those? If the V opens like it does in this picture, it is a minimum point. It is the lowest point on your graph. But we can also have absolute value graphs that look like this, in which case it would be a maximum. Okay? So it's your highest or lowest point. It's where the point of the V, all right, where the two sides change direction. The slope on the right branch is a 1. And we're talking, again, just about the parent function. The slope on the right side is 1. Rise 1, run 1. How about on the left side of that? What would the slope be on the left side? -1. Right? We had to go down 1 over. So this has a slope of 1. This has a slope of -1. That's always going to be the case with absolute value graphs. They're going to have slopes that are opposite. One will be a positive slope, one will be a negative slope. Okay? If we take points for x from -3 to +3, and we put them inside absolute value bars, the -3 becomes a +3. Yes? A -2 becomes a +2. But what happens to our positive values? They stay the same. So in your y column here, they're all positives. That's why we get the two branches. On the left side, a positive x gave us a positive y. On the left side, a negative x still makes a positive y. Okay? The common mistake, students draw a line and forget that it makes a turn. In other words, they start plotting points here maybe, and they're like, well, that looks like a line. I'm just going to draw a line through it. And they do this. And they don't find that spot where it changes direction. So finding that vertex is critical. Okay? I have to see on your graphs where that vertex is. All right. This formula here is, again, the algebraic way of saying absolute value. If our x value starts out being 0 or something positive, the absolute value graph, or the absolute value bars, don't do anything. If our x value starts out negative already, the absolute value bars will change it to its opposite. That's what that negative sign is. Okay? So, if our x is already a negative value, this is going to make it turn into the opposite of the negative, or the positive version. Okay? All right, so we're going to look at graphing our steps. Notice the way the function is written. Y equals a times the absolute value of x minus h plus k. We are going to start out by graphing the parent function. And again, we're going to do that for the first few. Once you see the pattern and then how we can shorten that up, we'll let you skip that piece. Okay? But for now, we're going to be graphing the parent function. We're going to look at what kind of transformations happen. What does this a do to my graph? It reflects it if it is negative, okay? So it reflects when it's negative. What else can it do? Yes. A vertical stretch or compression, depending on the size of that value. Okay? What does the H do? That is our left or right move, and our K value is our up and down move. So we're going to look at our equation and figure out what kind of transformations have we done to the parent function. And then we'll graph them. From our transformations, we will be able to tell where the vertex goes. We'll be able to figure out the equation for the axis of symmetry. And we'll be able to identify the slope of our graph. Now, there's not a single slope because it's not a line, but it's a V made up of parts of two lines. Okay, so they each have a slope associated with them. Okay, all right, let's try one. Our parent function again is y equals the absolute value of x. So we ignore all the transformations and we look at what that initial graph should be. What happens when we put -2 inside those absolute value bars? Becomes a 2. A -1 becomes 1. Anything 0 or higher stays itself? Okay. Plot those points. You don't have to draw the graph in. I just want you to see the V. All right, that is our parent function. What transformations have we done to it? What is this going to do? Right 2. So we've translated it right 2. And what else? Okay. So every one of our points we could shift right 2, up 3. Go ahead and do that. All right, so I'm going to start with the first one, the farthest one on the right here. Right 2 and up 3 puts it there. Every point you're going to move right 2 and up 3. What is the slope of the right side? And what we mean by that is we have that axis of symmetry, right? So what is the slope on the right side of that line? A positive 1. What is the slope on the left side? Okay. Where did the vertex land? This point? 2, 3. And my recommendation when you're doing these graphs is to make the vertex point a little larger than all your other ones, so you really define where it's changing direction. Okay. Axis of symmetry. How would I write an equation for that green dotted line? Vertical lines, how do we write them? X equals 2. It's always going to match the x coordinate from your vertex because it has to go through the vertex. Okay? All right. We have the same points that we had in our last one. Oops. So we're going to start with our same parent function. This time we've moved it where? Left 4. And down 1. Agree, disagree? Okay. So can we move those dots left 4, down 1? Yes? Have we changed the slope at all? So on the right, I still have a slope of 1, and on the left, -1. What are the coordinates of my new vertex? And the equation for the axis of symmetry? X equals -4. My question for you, could we have answered all of those questions without seeing the graph? It all comes right from the equation. Our vertex is going to be affected by left, right, up, down moves. We can identify that vertex location just based on our left and right, up and down moves. It is not affected by any kind of reflection. Think about it. Our initial vertex for the parent function is right on the x and y axis. So if we reflect over either one of those, it doesn't go anywhere. The only thing that's changing it is your left and right moves, your up and down moves. Even if we stretched it, what happens to our 0, 0 point if we multiply our y coordinate by something? To stretch or compress it, 1/3 of 0 is still 0. 2 times 0 is still 0. So the only transformations that are making that vertex move are your left, right, and up, down translations. So we can identify the vertex right from here. If we're going left 4, we're going to go to -4. If we're going down 1, we're going to move to -1 for our y coordinate. Okay? Can we identify the slope from the equation? What would change? What kind of transformation would change the slope? What would change the slope of that V? A stretch or compression? Yes? A vertical stretch or compression. Did we have one in this equation? No. So your slope is going to come from whatever that A value is. If there's a stretch or compression or a flip, a reflection over X, that's going to be evident from our equation, which means it affects our slope. Okay? So the slope of the right side is really going to come from that A value. And then our slope on the left is always just the opposite of whatever we had. All right, so let's try to graph some without actually plotting the whole parent function first. Okay? What kind of transformations do we see in this equation? Let's do them in order. Remember, we want to always go in order from left to right. What's the very first thing we see? A 1/2, which is a compression. So we know that we have a vertical compression by a factor of 1/2. Now, the effect that's going to have on my V is it's going to squash it down. So if this is my original picture, a 1/2 is going to look more like this. Okay? It's not going to be as steep. Because if we're compressing up to a 1/2, that means the new slope on the right side is going to only be a 1/2 instead of a 1. And the slope on the left side is going to be a -1/2. What's the next transformation we do? We know we have to go right 1 and down 4. Our vertex always started at 0, 0. If we go right 1 and down 4, we land there. What are the coordinates of that point? So right 1 moves us to a +1, down 4 moves us to -4. Okay? Axis of symmetry always has to go through your vertex. So if we know our vertex, our x value went to a 1, we know our equation is x equals 1. Yes? All right. So from our point that I've graphed, where our new vertex is, picture your line of symmetry being here. On the right side of that line, can we make a line that has a slope of 1/2? So from my vertex, I'm going to go up 1 over 2. Up 1 over 2. That's the right side of my V. On the other side, we want the mirror image. Up and back, up and back 2. Up 1, back 2. So we have one side that has a slope of negative 1/2. We have one side that has a slope of positive 1/2. Okay? So you should be able to graph these without even having that parent function plotted. Now that we've plotted it a few times, you know what it looks like. Yes? Okay. What do you think is going to happen with this one? I'm going to pause the recording for a minute. At your tables, I want you to identify all the different transformations that happen in this one. So in our equation, remember we talked about this yesterday. A negative 3 does two different things, right? You have to split it. What does the negative do? Reflect over the x-axis. Okay, then what? What does the 3 part do? Get in the habit of saying vertical stretch, because again, there are horizontal stretches and compressions. Vertical stretch by a factor of 3. And then what did we do? Left 2 and up 5. Okay. So again, looking at our equation, this right here is your answer here, right? That negative 3 is going to be the slope on the right side, which means the left side will have a slope of positive 3. Our left, right, up, down moves affect our vertex. So from the origin, if we go left 2 and up 5, what are the coordinates of that point? Axis of symmetry then would be x equaling negative 2. From your vertex point, you need to draw a line that has a slope of negative 3 on the right side. So we're going to go down 3 and right 1, down 3, right 1. Yes? To get the left side, we do the opposite. Instead of right 1, we're going to go left 1. So down 3, back 1, down 3, back 1. It should look symmetric. Yes? Here is your line of symmetry. Does it look the same on each side? Yes. So if you know what the right side looks like, can you flip it over that line, get the left side? All right. And try to hit your dots. Make a nice line. All right. Why did it open down? Because we reflected it. Yes? Okay, now I'm going to take one point from that parent function. Okay? I'm going to pick one point. Let's say we pick this point. Okay? Does it move and land on my new graph if we were actually moving individual points? The first thing to do is reflect it over the x-axis, which puts it here. Then I'm going to stretch it by a factor of 3. Well, right now it's at negative 3. If I multiply that by 3, I'm down here at -9. And then it says I have to go left 2 and up 5. So it's fitting what we said it should fit. Yes? Okay. The last piece that we're going to look at, we are going to rewrite equations so that they are in the format that we've been using. All right? That format has to look like this. If our equation is not in that form, we can't identify all the things we've been talking about. So we have to do a little converting sometimes. To do that, we are going to use factoring. Okay? In our formula, we want a single x inside that absolute value. We have a 2x. We are going to factor that 2 away from the x. It's important to note that at this point, we still are working inside the absolute value bars. We're just going to factor this part of it. So 2x plus 4, if I factor out a 2, leaves me what? X plus 2. Now I can take this and pull it out, and it will become the a part of my formula. Okay? When you pull it out, though, you have to take its absolute value because it's still inside those bars. So what's the absolute value of 2? Okay, so we get y equals 2, and then the absolute value of x plus 2, and then minus the 3. Okay? What is the slope? This 2 is the slope on the right side. Left side will be -2. Where's the vertex? Careful. Which way did we go? Yes, we're going to -2, -3, because we went left 2 and down 3. Okay. The 2 in front was a vertical stretch. All right. Axis of symmetry. X equals -2. It needs to be a whole equation, not just a number. All right. So finding our vertex at -2, -3. On the right side of that, we want to make a line that has a slope of 2. So up 2 over 1. We want to do the reverse on the other side, up 2 and back 1. And draw it in. Make sure that you have arrows at the end. All right. How is this different? Yeah, instead of x minus h, our x is the second term. Can I rewrite it like this? Is that the same thing? Yeah, the 3 is still negative, the 9 is still positive. I've just changed the order of them. What is it that I need to factor out so that I just have an x? I have to take a -3. When I factor it out, it's still inside the absolute value bars. I'm just factoring it away from the x. What's the remaining piece from this 9 if I factor out a -3? Okay. Now, when I pull that -3 out of the absolute value bars, it becomes a 3. All right, I'm going to pause the video for a second. Go ahead and finish this example. All right, so first transformation should have been a vertical stretch by a factor of 3. So our slope now is 3 on the right and -3 on the left. We have also gone to the right 3 and up 5. We've done that kind of translation. So right 3 up 5 puts me at the point 3, 5. Axis of symmetry should be x equals 3. Okay. Plotting our points. We go to 3, 5. There's our vertex. We're going to do a slope of 3 on the right side and a slope of -3 on the left side. All right. The last question is the reverse. I've given you the picture. I want you to write the equation. All you need to do is figure out the vertex and the slope. Where did the vertex move to? Our parent function was here at the origin. Which way did we go? We went left 1 and up 4. All right, so the vertex has coordinates -1, 4. Yes? All right. What's the slope? Now remember, in our equation, it's the slope on the right side. So we have to be looking at the slope of this part. We're going down 1 and over 3. So our slope is -1/3. Again, make sure you're using the right side of your picture. Okay? Can we write the equation now? Y equals -1/3. The slope on the right, absolute value. We want to go left, so we need x plus 1. And we want to go up 4. Does that make sense? All right. So, once again, hang on. All right. I'm giving you both days assignments. You're going to turn this in as one assignment on Monday. Tomorrow you will have work time on it after you finish your formative quizzes.